Your legs are underwater and rising fast. You are standing inside a wooden warship on Lake Poyang in 1363 AD, and a crossbow bolt just punched a hole through the hull 3 feet below the waterline. Cold lake water is pouring in through that hole every second. The deck above you is on fire, and your captain just gave you 40 seconds to stop the ship from rolling under. No engine, no electric pump, no steel hull, just a wooden foot pedal and a wall carved with a hidden hole that most sailors on Earth in 1363 AD had never even seen. That hidden hole came from copying a plant. A 1,000-year-old trick borrowed from a stalk of bamboo let this crew do something no European ship could do for another 400 years. Block a catastrophic breach inside one isolated room, continuously dump thousands of gallons of floodwater overboard under live fire, and keep fighting. Here is how ancient shipwrights engineered a ship-wide survival system that could outlast a battle emergency, starting with the wall that stopped the flood before it ever reached the pump. Look inside a European sailing ship from 1200 AD and you see a hollow rib cage, long wooden ribs curved from keel to deck with 0 internal dividers separating bow from stern. A rock tearing open the hull near the bow floods the entire open floor from front to back. Chinese shipwrights rejected this open design after studying the natural geometry of a bamboo stalk. Internal cross walls or nodes prevent a hollow bamboo tube from collapsing under bending stress. Shipwrights duplicated that structure inside their hulls. Instead of wide open bays, they constructed solid transverse bulkheads spaced 2 to 3 meters apart. Imagine a long wooden box divided into 6 isolated chambers using heavy timber walls. Each divider anchors directly to the floor, ceiling and side hulls, forming an airtight, watertight bulkhead. A ship riding ocean waves gets pushed up in the middle and down at both ends, a force called hogging. Then the wave rolls the other way, pushing the middle down and both ends up, a force called sagging. An open ribcage hull has nothing stopping the wood from twisting under that back and forth stress. A hull filled with 12 to 16 solid bulkheads acts like a stack of rigid picture frames glued into a tube. Engineers call this a box girder. Push down on one frame and the force spreads sideways into the next frame, instead of bending the whole tube. Divers exploring the 13th century Quanzhou shipwreck found 13 separate watertight holds inside a single hull, each one sealed by a solid wooden wall nearly 2 inches thick, bolted together using iron nails. That ship carried cargo for years across pirate-infested waters and violent monsoon storms without snapping in half. Building solid walls inside a ship creates a brand new problem. Rainwater and seawater spray still leak into every single sealed compartment during normal sailing. If that water gets trapped with nowhere to go, it rots the grain cargo and throws off the entire balance of the ship. The crew needed a way to drain water across walls built specifically to block water. That contradiction almost sank the entire design before it ever left the shipyard. A ship leaks constantly, even with no battle damage. Rain falls on the deck and seeps through seams. Waves splash over the gunwale. Humidity condenses inside the hull. If that water sits trapped inside a sealed bulkhead compartment, it soaks the wooden floorboards, breeds rot, and slowly weakens the entire hull from the inside out. Shipwrights solved internal moisture management using a simple low-point drainage channel. Consider 6 water basins lined up side by side, divided by solid walls. Small arch-shaped cuts at the base of each wall allow accumulated water to trickle down into a single central sump at the lowest point of the hull. Shipwrights carved these openings, called limber holes, into the base of every bulkhead, right where the timber met the keel. During routine sailing, bilge water from every compartment drained through these arches into the central sump, where it could be pumped out. Before entering combat or navigating dangerous reefs, sailors hammered fitted wooden plugs wrapped in oiled cloth into the limber holes. This preemptively locked every compartment shut. When an enemy missile breached an outer hold, the flooded compartment was already isolated, preventing seawater from ever reaching the adjacent holds or the central sump. Marine archaeologists diving the 1323 AD Shinan shipwreck off the coast of Korea found this exact system intact. Transverse bulkheads with base limber holes, built specifically for controlled drainage, sat on the ocean floor for nearly 700 years, still showing the carpenter's original cuts. This system solved the water management problem, but drainage alone does not remove water from a ship. Water sitting in a central sump still weighs the vessel down. If that sump fills faster than the crew can act, the ship settles lower and lower into the water until the deck disappears beneath the waves. Something had to physically lift thousands of gallons out of that pit and throw it back into the sea, and human arms alone could never move fast enough to keep up with a real battle breach. In a real hull breach during combat, floodwater does not trickle in politely. It surges through a jagged crack the size of a dinner plate, dumping hundreds of gallons into the sump every single minute. A hand-cranked piston pump, the kind European sailors use for centuries, moves water in short bursts, one small squirt at a time, with a pause between every stroke. That pause is a death sentence in a fast-flooding hull. Chinese naval engineers solved this using a continuous loop conveyor system. The pump uses a heavy wooden link chain carrying square wooden pallets, fitted inside an inclined wooden trough. The chain loops continuously around two gear wheels, one submersed in the flooded sump and one mounted on the deck above. This device is called the Square-Pallet chain pump, and understanding its mechanics takes three moving parts. First, the trough sits mounted inside a steep wooden shaft, running from the flooded sump up to an open scupper port on the upper hull. Second, a wooden chain loaded with square paddles runs the full length of that shaft in a closed loop, never stopping, never reversing. Third, 2 to 4 sailors stand on a raised wooden platform above the trough, pressing foot pedals connected to a central axle with a toothed sprocket wheel. When a sailor presses down with his foot, the sprocket wheel turns. The turning sprocket pulls the wooden chain forward, dragging each square paddle up through the trough like a conveyor belt. Each paddle fits tightly against the trough walls, trapping a solid slug of water in front of it, and pushing that water straight up the incline. By the time one paddle reaches the top and dumps its water out the discharge port, the next paddle is already scooping up a fresh load at the bottom. This continuous motion produces an unbroken stream of water. Operating in tight four-man shifts, a single pump crew could continuously discharge over 150 gallons of floodwater every minute, removing over 1,500 gallons during a critical 10-minute battle emergency without losing prime or stopping to reset. The mechanism worked because human leg muscle, the strongest muscle group in the body, powered a continuous loop instead of a jerky back and forth stroke. Even the strongest chain pump in the world could not save a ship whose wooden seams were tearing open faster than the crew could plug them. The wood itself needed a chemical weapon against water pressure, and that weapon came from an unexpected source: tree sap. The outer hull of a warship contains hundreds of feet of plank-to-plank seams. Ocean waves continuously twist the hull, prying these seams open by fractions of an inch with every roll. Under this constant mechanical stress, traditional rope caulking rots and disintegrates within a single sailing season. Shipwrights needed an elastic sealant that could penetrate hairline gaps and cure into a flexible, waterproof binder that expanded and contracted alongside the timber. The solution came from mixing three ordinary materials. First, slaked lime, a white powder made by burning limestone and adding water. Second, raw tung oil, pressed from the seeds of the tung tree. Third, chopped ramie hemp fibres, the same tough plant fibre used in rope. Tung oil is packed with unsaturated fatty acid molecules, meaning the molecular chains inside the oil have loose reactive bonds. When shipwrights mixed that oil with slaked lime and exposed the paste to air, those loose bonds reacted with oxygen and linked together into longer and longer chains, a process called oxidative polymerization. Thousands of tiny hooks slowly latch onto each other until the entire liquid paste transforms into a solid, rubbery film. The chopped hemp fibres reinforce that hardening paste the same way rebar reinforces concrete, giving the finished seal enough tensile strength to stretch slightly under wave stress without cracking. Shipwrights called the finished compound Chunam, and they packed it into every hull seam, every bulkhead joint, and every nail hole across the entire outer planking. This chemical seal solved leaking at the seams, but Chunam only protects a ship that stays intact. No sealant on Earth stops a wooden hull from cracking open when a warlord's fleet launches a direct assault with trebuchets, fire arrows, and boarding hooks. Every system built so far, the bulkheads, the limber holes, the chain pumps, and the chemical seals, was about to face its ultimate stress test on the open water of a lake at the center of an empire. On August 29, 1363 AD, two fleets collided on Lake Poyang, and the engineering discussed so far became a matter of life and death for over 500,000 men. Warlord Chen Yuliang commanded roughly 200,000 troops aboard massive three-story tower ships called Longjiang, each one wrapped in wet hides and iron plates, armed with siege trebuchets bolted directly onto the deck. Facing him, rebel leader Zhu Yunjiang commanded a fleet only one-third the size, built from smaller, faster vessels. On paper, this battle should have ended in minutes. Chen's floating fortresses towered over Zhu's fleet like castles looking down on rowboats. Bigger ships meant heavier ships, and heavier ships meant deeper hulls, which meant more surface area exposed to underwater damage. On August 30th, Zhu's flagship ran aground on a shallow sandbar directly in the middle of the engagement, taking direct hits from Han catapults while stuck fast in the mud. Every bulkhead, every limber hole, and every foot pedal pump aboard that grounded ship kept working through the barrage, holding the hull together and keeping lake water out of the lower decks while the crew fought for their lives above. Sailors aboard Zhu's ships deployed a terrifying incendiary weapon called the No Alternative, a reed mat cylinder packed with gunpowder, iron shot, and incendiary bomblets, mounted on long thrusting poles to ignite enemy rigging and wooden decks on contact. Han catapults answered back with heavy stone projectiles that could crush a wooden hull on direct impact, testing every inch of that box girder bulkhead architecture. Then on August 31st, the wind shifted hard to the north. Zhu ordered small, expendable ships packed with oil-soaked reeds and gunpowder to be set ablaze and steered directly into Chen's fleet, where the massive tower ships sat chained together in a tight defensive formation. That tight chain formation, meant to protect against boarding, became a death trap once fire took hold. Flames leapt from ship to chained ship, and within hours, Chen's numerical advantage turned into burning wreckage scattered across the lake. The battle ground on for 36 days total, ending only when Chen Yuliang took an arrow through the skull while attempting a final breakout on October 4th. His fleet, once the largest force on the lake, collapsed into surrender. This victory secured Zhu Yuanzhang's control over the Yangtze River basin and set him on a direct path toward founding an entirely new imperial dynasty. Winning a river war and building a global naval empire are two very different engineering challenges, and the ships that would soon sail across the Indian Ocean needed infrastructure that didn't even exist yet. Once Zhu Yuanzhang secured his empire and became the Hongwu Emperor, his successors faced a new tactical problem that had nothing to do with combat. Massive wooden warships need constant maintenance. Barnacles slow down a hull. Wooden planks rot below the waterline. Bulkhead seals crack over months of ocean exposure. None of these repairs can happen while a ship floats in open water. Engineers at the Longjiang shipyard near Nanjing solved this maintenance problem using a mechanism as old as the tide itself. Shipwrights excavated massive rectangular basins along the riverbank, measuring hundreds of feet long and fitted with heavy timber sluice gates facing the Yangtze River. At high tide, workers opened the gate, letting river water rush into the empty trench until the water level matched the river outside. A massive warship floated directly into the flooded trench under its own power. Workers then sealed the gate shut, trapping that water inside the trench like a giant bathtub. As the tide naturally receded outside, the water trapped inside the dry dock had nowhere to go, but back out through a lower drainage channel, slowly lowering the ship down onto sturdy wooden blocks positioned along the trench floor. Within hours, the entire basin sat completely empty, leaving the ship's hull fully exposed in dry, stable conditions. Shipwrights walked underneath the keel, replaced damaged rudders, and repacked Chunam seals into every bulkhead joint without a single drop of water interfering. This tidal dry dock system provided industrial-scale maintenance facilities long before enclosed dry docks became standardized in Renaissance Europe, such as England's Portsmouth Dry Dock, built in 1495. The Longjiang facility became the maintenance backbone for Admiral Zhang, his legendary treasure fleet, giant Baochuan ships stretching over 400 feet long, each one packed with 12 to 16 transverse bulkheads inherited directly from centuries of bulkhead engineering refined on Chinese rivers. Centuries later, in 1787 AD, Benjamin Franklin wrote a letter urging the American government to adopt Chinese-style watertight bulkheads on mail packet ships, warning that Western vessels were sinking unnecessarily due to their open, uncompartmented hulls. British naval engineer Sir Samuel Bentham took the idea further in 1795 AD, designing experimental Royal Navy ships using the exact bulkhead geometry first carved into bamboo-inspired hulls over 1,000 years earlier. Every piece of this puzzle, the bulkheads, the limber holes, the chain pumps, the Chunam sealant, and the tidal dry docks, worked together as a single integrated survival machine. Ancient Chinese shipwrights built a chain of small, physical solutions, each one solving the exact failure point of the system before it, and that chain of solutions kept warships floating through storms, battles, and centuries of ocean crossings that should have sent them straight to the bottom.